We're going to talk about solving exponential and logarithmic equations. And this can be done both algebraically and graphically. I want you to still do it algebraically, but feel free to check your answers doing it graphically, although there are some problems that will only be done graphically. So let's do an example of how you solve an exponential function. To solve an exponential function, the first thing we're going to do is make sure that the exponential term is isolated. That means that there is nothing else being multiplied to it, divided, added, or subtracted. Nothing else is attached to the exponential term being the 3x to the, raised to the x plus 2. In order to solve this, what we're going to do is we're going to start by putting log on both sides of the problem. What then happens is that exponent of x plus 2, using the law of logs, can be brought down and multiplied in front of the log of 3. Now, since this is being multiplied, to get rid of the log 3, we're going to divide both sides by log 3. Now remember, this is a log base 10, so this is something that can be evaluated in our calculator. And then the last thing that's going to happen is we're going to take this 2 and we're going to subtract it from both sides. So in your calculator, you'll do the log of 7 divided by the log of 3 minus 2. And you should get approximately negative 0.2288. If you want to check this using your graphing calculator, what you would do is you would put into y1 equals 3 raised to the x plus 2, put into y2 equals 7, graph it, and then find the point of intersection using the intersect function. Let's solve the equation 8 times e to the 2x equals 20. In order to solve this problem, I had said a moment ago that we want to isolate the term with the exponent. Here's the term with the exponent. In order to isolate it, we're going to need to divide both sides by 8. Don't worry about reducing that fraction. We'll worry about getting rid of it later. Now that the exponential term is isolated, we're going to take the log of both sides. But since the base of this exponent is e, we're not going to use log base 10. We're instead going to use ln. Because the natural log and e cancel. So now we're left with 2x is equal to the natural log of 20 over 8. The last step is going to be to divide by 2. So you're going to do the natural log of 20 over 8 and then divide that answer by 2. And you should get approximately 0.458. And again, you can check this in your calculator if you plug this side of the equation into y1 equals, this side into y2 equals, and find the point of intersection. For this particular problem, you would have to change the window because when you graph y equals 20, the standard viewing window only goes up to 10, so you may want to change it, the y maximum to 25, because sometimes the calculator's a little testy. If it doesn't see the point of intersection on the screen, a lot of times it won't find it for you. Almost all these problems can be solved either graphically or algebraically. For the purpose of this video, I'm going to do everything algebraically, but I showed you how to do it graphically in class, so I'll mention it as we go along. I want to solve e raised to the 3 minus 2x equals 4. First, is our exponential term isolated? Yes, it is. If it's isolated, then I'm ready to put a log on both sides. Since the base is e, we're going to put the natural log on both sides. And this cancels. So I'm left with 3 minus 2x is equal to the natural log of 4. Well, now I'm going to finish solving for x. We're going to subtract the 3, and then we're going to divide everything by -2. So in my calculator, I'd first do the natural log of 4. I would subtract 3, and then I would divide that answer by -2. And you should get approximately 0.807. And again, if you want to put in your calculator, you would put this into this into y1 equals, this into y2 equals, and find the point of intersection. Let's look at a different type of exponential function. This particular exponential function is a function that looks like it's in quadratic form. Kind of looks like a quadratic. You know, where you define two numbers that multiply to give you -6, but those same two numbers have to add to give you -1, and you find out that it's -3 and +2. But instead of using x minus 3 and x plus 2, we're going to use e to the x minus 3 and e to the x minus 2. What ends up happening is we use the zero product property to set up two equations. So the first equation is e to the x minus 3. E to the x equals 3. You take the natural log of both sides, and when you do that, this cancels. You're left with x is equal to the natural log of 3, which is approximately 1.0986. Now, when you come and do this equation, e to the x plus 2 equals 0, so e to the x is equal to -2. The exponential function e, when you raise it to a power, will never be a negative. Because remember, we found out that e is a real number. It's 2.91 or 2.82, whatever it is. You can't raise it to a power and get a negative, so this problem just doesn't happen. Now, if you don't like doing it this way, that's fine. Notice the way this equation is set up. It's equal to 0. If you graph the e to the 2x minus e to the x minus 6 in your calculator, you want to find where the graph hits the x-axis. In other words, you want to find the 0, and you should find this as the 0. Sometimes we're given an equation where we have to factor things out first, like a greatest common factor. In order to solve 3x e to the x plus x squared e to the x equals 0, I want you to notice that both terms share an x and they share an e to the x. So I'm going to factor both of those out. I'm left with 3 plus x. Well, what I can do now is I can use the zero product property to finish solving for x. So first I'm going to take x and set it equal to 0, so that's one of the solutions. And then I'm going to do e to the x is equal to 0, which can't happen because you can't raise e to a power and ever get 0. If you raise e to the 0 power, you just get 1. And then we're going to set 3 plus x equals 0, so x equals -3 is my other solution. If you had graphed this equation, you would have seen it hit the x-axis at two places. It would hit the x-axis at 0, and it would hit the x-axis at -3. Now let's change what we're solving. Let's do some logarithm problems. The exponential functions, to solve them, we put a log on both sides. So to solve log problems, we're going to rewrite them in exponential form. So in order to solve the natural log of x equals 8, remember that the natural log is the log base e of x equals 8. In exponential form, it's going to be e to the 8th equals x. And e to the 8th is approximately equal to 2981, approximately. The second equation, the log base 2 of 25 minus x equals 3, we're going to put it in exponential form. Remember, the base is 2, the exponent is 3, and that's going to equal 25 minus x. So 8 is equal to 25 minus x. X plus 8 is 25, and X is equal to 17. The same property, or the same thing that we did with exponential functions, we're going to do with logarithmic functions. In order to solve a log function, it first needs to be isolated. That means I got to get rid of anything that is not with the log 2x. Well, there's a 4 that needs to get subtracted first. Remember, when we're solving equations, we always get rid of something that we can add or subtract first. Now I can get rid of that 3 by dividing. Now that the log is isolated, I can rewrite this in exponential form. Remember, if you don't see a base, it's 10. So 10 to the 4th equals 2x. 10 to the 4th is 1, 2, 3, 4. And divide by 2, and you find out that x is 5,000. In order to solve a log equation, sometimes we have to combine logs first, using our laws of logs. In order to solve a log equation, you can have no more than one single log on either side of the problem. So on the left-hand side of the problem, I have 2 logs. Well, since they're being added, I'm going to simplify it by multiplying the x plus 2 times the x minus 1. Well, x plus 2 times x minus 1 is x squared plus x minus 2. Now I'm going to put this in exponential form. The base is 10, so 10 to the 1st is equal to x squared plus x minus 2. This is just a quadratic equation, and in order to solve quadratic equations, it has to be equal to 0. So I'm going to subtract the 10 from the other side. Now you have 2 choices. You can either graph this quadratic and find where it touches the x-axis. That's one way of finding the solutions. Or, for the purpose of this video, I'm going to factor it. The 2 numbers that multiply to give you negative 12, but add to give you 1, are 4 and negative 3. So x must equal negative 4 and positive 3. I'm not done, though, because we cannot take the log of a negative number. So if you can plug either of those numbers back into the original problem and it gives you a log of a negative number, it cannot be a solution. Well, look at what happens when you plug negative 4 back in. You would get the log of negative 2 plus the log of negative 5. Can't have the logs of negatives. 3, however, is fine. That is the only solution. Some problems are just so nasty that you don't want to try to do them algebraically. This is a problem that I would say we're just going to do graphically, because there are x's on both sides of the equation. I'm going to put this into y1 equals, and I'm going to put this into y2 equals, and I'm just going to find where the graph intersects. Now, here's the thing. Sometimes they intersect in more than one location. And you can actually see both intersection points on the screen. In order to find both intersection points, when you go to the intersect function, before you hit enter 3 times, move the cursor close to the intersection point you want to find, then hit enter 3 times. So you should find that one of the solutions is at negative 0.71 approximately, and the other solution is at 1.60. Let's do a word problem. If I sub 0 and I denote the intensity of light before and after going through a material, and x is the distance in feet the light travels in the material, then according to the Beer-Lambert law, negative 1 over k natural log of I over I sub 0 is equal to x, where k is a constant depending on the type of material. I want to first solve this equation for k. Now, in order to do that, the first thing that I'm going to do is notice that this is a fraction. And the easiest way to get that k out of the denominator is to multiply the other side of the equation by the reciprocal of negative 1 over k, which is negative k over 1. So the first thing I'm going to do is I'm going to multiply the other side of the equation by the reciprocal. So I'm going to get negative k over 1 times x. Now all I have to do to finish this problem off, to solve, is to divide by negative x. And then all of this goes away. All right, let's go to B. For a certain lake, K is equal to 0.025, and the light intensity is I sub 0 equals 14 lumens. Sorry, I couldn't write I sub 0. That's what I mean. Find the light intensity at a depth of 20 feet. I know that this is 0.025. And I know that the initial intensity is 14, sorry. What I want to find is the intensity after the light has traveled 20 feet. All right, the best way to go about solving this is to first, let's multiply by the reciprocal of that negative 1 over k. We're going to get negative 0.5. So I'm going to do this in another. The natural log of I over 14 is equal to negative 0.5. Since that's a natural log equation, in order to solve it and get the variable that I'm trying to find out of the natural log, we're going to rewrite an exponential form. So e to the negative 0.5 is equal to I over 14. Then to finish solving the problem, you just have to multiply e to the negative 0.5 times 14. And you should get 8.49. The further into the substance you go, the less intense the light is going to be. Let's go back and talk about some compound interest problems. But what we're going to be doing is we're going to be instead finding time, which is in the exponent. So we're going to have to use our properties of exponential functions in order to get the time t out of the exponent. A sum of $5,000 is invested at an interest rate of 5% per year. Find the time required for the money to double if the interest is compounded to the following method: semi-annually and continuously. First of all, semi-annually means twice a year. It also means I'm going to have to use this formula. Now we want to double our money. So if I start with $5,000, when I double it, I'll have $10,000. The rate is going to be 0.05. Semi-annually means twice a year, and then raised to the 2t. So what I'm going to do is first I'm going to divide by 5,000, and I'm going to get 2, which is interesting because I'm doubling my money. Then I'm going to do 1 plus 0.05 times 2, which is going to be, oops, that's not what I wanted, 1.025 to the 2t. This is an exponential function, and I need to get t out of the exponent. So we're going to rewrite this in log form. So it's going to be the log base 1.025 of 2, that's the exponent, equals 2t. Now, you have two methods for evaluating the log base 1.025 of 2. If you have the new operating system on your calculator, under the math function, you can use that log function. Or you can just use the base change formula, which is going to be the log of 2 divided by the log of 1.025. And then you're going to take that answer and divide it by 2. And you should find out that it's going to take approximately 14.04 years for your money to double. Now let's do this again if we want to find continuous compounding. Remember, continuous compounding is the PERT formula. So I still want to double my money. So I want $10,000 if I start with $5,000. And my rate is still 5%. In order to solve this problem, first I'm going to divide by 5,000, and I get 2. And then, to get the t out of the exponent, I'm going to take the natural log of both sides, which cancels over here. So you're left with the natural log of 2 is equal to 0.05t. And then I'm going to divide both sides by 0.05. And I'm going to find out that t is approximately 13.86 years. There's not a ton of difference in the amount of time, but continuous compounding is shorter. Last problem, a sum of $1,000 is invested in an interest rate of 4% per year. Find the time required for the amount to grow to $4,000 if interest is compounded continuously. Okay, so if interest is compounded continuously, I'm going to use the PERT equation. I'm starting with $1,000, so that's my principal, and I want to end with $4,000. And my interest rate, 4%, is 0.04t. This problem is solved exactly the same way as the last problem. First, you would divide by 1,000. 4,000 divided by 1,000 is 4. And then you would take the natural log of both sides, and as you know, the natural log is going to cancel e. So I'm skipping a step now. And then I'm going to divide by 0.04. And I'm going to find out that it takes approximately 34.66 years for my money to go from 1,000 to 4,000.